Oh, yes, very good. I did hear that last year, and I was giving some random examples. Just one quick mention on example 6. I mentioned that there are remote stretches of highway where they do this. The mile markers have cameras that take pictures every so often. But a more salient example that happens every weekend on TV is in pit. You want to explain it?
On pit road in NASCAR, they have a set speed limit, but they don't actually have speedometers in their car, so they just have to use timing zones. They have like 6 different timing zones, and if you go through it too quickly, then they know that you sped, and so they know to penalize you. So, yeah.
That's exactly right. So NASCAR, every single race uses the mean value theorem to assess the speed of the drivers coming into pit road. Yeah. What's that? Speaking of Talladega Nights, it's classy, and it says, I love to party. All right, example 7. Example 7. Let f of x be a function that is differentiable where? Everywhere, for all x, which means it's also what everywhere? Continuous. Okay, cool. So it's smoothly connected everywhere. Suppose that f of 0 equals -3, and that f prime is less than or equal to 5 for all values of x. How large can f of 2 possibly be? I don't know. Let's ask f of 2. How large can you possibly be? As big as I want to be. That's good, f of 2, but we need a number. Okay? We can't just speak in hopeful aspirations. How are we going to do that?
Just assume that it has to be a slope of half, so 5.
Yes. If the slopes, it says the slopes are less than or equal to 5, and we want to know the maximum value, we could assume that it's increasing at the maximum rate the whole time and see what the new y value would become, right? So let's look at a little picture here. A little picture. That's actually too small. You can't see that. Let's go with a bigger picture. F of 0 equals -3. That's right here, okay? And we want to know how big f of 2 can possibly be. So what we're going to be doing then is we're going to be going from x equals 0 over to 1 and then over to 2. And if we want to know the largest possible value that we can have at 2, let's just go up, as Rapp said, at the maximum allowable rate, which is 5, yes? So if I did that, I would go up 5 from -3, which puts me where? At 2, and then I would go right 1. So now I'm at the point 1, 2. Everyone agree? Up 5 over 1. That's the slope, up 5 over 1. And since we're trying to get to 2, we'll do it again. So I go up 5 more, which puts me at where? 7, and I go over 1, and now I'm at 7. So the maximum value of f of 2 has a maximum value of 7. And of course, if the slopes go up any less than that, it would fall somewhere less than 7. That's not a bad problem to do intuitively, right? If you sketch a little graph, just go up 5 over 1. Assume the maximum rate. Why the heck does this show up in a mean value theorem section? Good question. Well, we have 2 points. 2 points. We could actually set it up as f of 2 minus f of 0 all over 2 minus 0. And we can plug in what we know. We're trying to find f of 2. So f of 2 stays there. Do we know what f of 0 is? It's -3. So when we subtract -3, we really get +3, right? All over 2. Now, because it's differentiable everywhere, we know that that has to equal the derivative somewhere. Yes? But if we then know that the derivative has to be less than or equal to 5, then that means that if this is the derivative, that also has to be less than or equal to 5, yes? So you can kind of set up an inequality. You could say that f of 2 plus 3 over 2 has to be less than or equal to 5. The average rates of change have to be less than 5 as well. Okay? And you can set it up as an inequality. Now, if you solve, multiply both sides by 2, you get what? 10. And then you subtract 3 from both sides, and you get 10 minus 3, which is 7. And now you get f of 2 can be less than or equal to 7. And that kind of says the same thing, right? If you say f of 2 is less than or equal to 7, you're saying 7 is the maximum it could be, but it could be anything smaller. So it kind of sets up as a mean value theorem ratio, because you're relating an average rate of change to an instantaneous rate of change. So go ahead and answer B using the mean value theorem. And while you're doing that, I'll sketch my reasonably sized graph so we can interpret it graphically. But try to do it using the mean value theorem. I don't even know if I did it right. I'm graphing. This one's a little bit tricky if you try to do a graph, but that's why I wanted y'all to try and just do it mechanically now that you kind of know how to do it. This makes good multiple choice type questions. Good, good, good. So setting it up with the mean value theorem, you still want to get in the habit of doing final minus initial. And so if we're looking at the x values 1, f of 1, and f of 5, the x values are 1 and 5. So if I'm setting it up, I would say f of 5 minus f of 1 all over 5 minus 1. We know that's equal to f prime of x for some x. But we also know that f prime has to be greater than or equal to negative 3. So if this is f prime, then we can set that greater than or equal to negative 3. And now we plug in what we know. F of 1 is the mysterious value, so we'll plug in everything else. F of 5 is 2. So 2 minus f of 1. Of course, the bottom is 4, right? So if you multiply both sides by 4, you get greater than or equal to negative 12. And so you get negative f of 1 is greater than or equal to, subtract, you get negative 14. And of course, how do we solve that? Multiply both sides by negative 1, and we remember to do what with the inequality? Flip it. So there you go. F of 1 is less than or equal to 14. Now, if you look at it graphically, notice we're working backwards. This is where you have to really orient yourself. We know that f of 5 is positive 2. We know that the slopes at most are negative 3. That's a negative slope. That means they're going downhill. What's the largest possible of f of 1? So that's kind of like going back in time. So if we know that our slopes are going downhill from 1 to get to the value of 2 at 5, we know we have to start higher. So working in reverse, instead of going with negative slopes, down 3 over 1, you work backwards. Up 3 over 1, up 3 over 1, up 3 over 1, up 3 over 1. And again, you go at the maximum magnitude rate. And you go basically up 3 times, or you go up 4 times. So you gain 12. So if you add 12 back to your starting value of 2, you get 14. So either way to answer that question is fine. But it is a nice little application of the mean value theorem where you relate the average rate of change to the instantaneous rate of change. The mean value theorem can also be called the IVT for derivative functions. The IVT guarantees y values of a function, and the MVT guarantees derivative values. So you can think of the MVT for as the IVT for derivatives, for slopes. All right, we be done. Any questions? Have y'all looked at the worksheet? No. Let's I can't remember if I did this. While we're still recording here, let's do something else. Y'all remember when we talked about the IVT? How long ago was the IVT? 1.5? That was a long time ago. Let's take a look at what that was. There was a problem at the end, which was from a modified test question from the 2007 exam. Let's go ahead and pull up the 2007 exam. How are we going to do that? I'll do it from my Google Drive. I want to pull it up. So just follow along. You could actually search for it on Safari if you want to go to AP Central. You can pull up the 2007 AB exam. I have it here on my hard drive, which might be a little bit faster. It's in so many subfolders, though. 2007. I'm going to pull up the scoring guidelines. Huh? We're printing? Yeah, it's changed. Okay, so here we are. We have it loaded. Remember, this was the lowest scoring question, 0.95 or 0.94, something like that. The average score was not even 1. So we looked at the first question. Explain why there must be a value between 1 and 3 where h of r equals -5. It's probably worth looking at that again. Yeah? Let's do that. Let's look at part A. Let's just do part A and B, okay? We're ready. The values f and g are differentiable for all real numbers. That means they're also continuous, right? So the derivatives exist and the functions are continuous. G is strictly increasing. G is strictly increasing, so G prime must be positive everywhere, not just on the values given. The table gives values for the functions in the first derivatives. The function h is given by this. All right. H is a composition of two continuous functions. So is h itself going to be continuous? Yes, that was the big deal back in 1.5. If you compose two continuous functions, you get another continuous function over their domain. So, and don't forget the -6, that is part of it. So part A, explain why there has to be an r value between 1 and 3, such that h of r equals -5. We're trying to guarantee that a particular y value exists. Anytime you're trying to guarantee a particular y value exists, guess which theorem you're going to use? IVT, okay? R is a what type of value, x or y value? It's an x value. So that's what threw some people off. They're using funky letters here. But it's just an x value. Show that there's an x between x equals 1 and x equals 3, where the y value there equals -5. Okay, so what's your argument going to be? H of x is continuous on the closed interval. What closed interval? They gave me an open interval. Remember, they're just saying the solution that we're looking for will not be one of the endpoints. But for the IVT to work, it has to be continuous on the closed interval. So you'll say h of x is continuous on the closed interval from 1 to 3. So the IVT applies. You can do that right away. You can invoke the name of the IVT and get credit. So now remember, it's all about the computations and the inequality. For the IVT, you figure out what the values, the y values are at the endpoints. Remember doing that? All right, let's do it. H of 1 is going to be f of g of 1 minus 6. F of g of 1 minus 6. That's not really good for a comparison. So now we pull our values from the table. G of 1 is 2, and then f of 2 would be 9. So this becomes 9 minus 6, which is 3. And you could do it. You could do that much in your head. Just pull tables out, table values out. H of 3, I would write it out as f of g of 3. At Thanksgiving, that's the time to pull the tables out, because usually you have a lot of tests. And you put tables where you normally don't have tables. We don't have room in the living room anymore. We've already overloaded. So go ahead and set up a little card table in the bathroom. Who gets to sit there? The people who are late. That's right. All right. F of g of 3. What's g of 3? 4. So now what's f of 4? Negative 1. What's negative 1 minus 6? Negative 7. We're trying to prove that what y value exists? Negative 5. There's no way to go from x equals 1 to x equals 3 as we go from y equals 3 to negative 7 through a continuum without passing through what value? Negative 5. So how about this? How about since negative 7 is less than negative 5 is less than 3, the values that we found basically hem in on either side the value we're looking for, comma, by the IVT. I'm going to throw it in there again. By the IVT, and then what do? We reuse their values, their words, sorry. There must be a value R such that. We rewrite all that right there, okay? Easy. Use their terminology. By the IVT, there must be a value R for 1 to 3 such that h of R equals negative 5. Got it? How many points would you expect to get for that? They gave you 2. Hey, you got 2. And remember, if you got 2 at this point, you're already like more than double the national average. Wow. All right, so where did the 2 points come from? Computing h of 1 and h of 3. That was pretty easy. And then your conclusion using the IVT. Let's see what they did. Since h of 3 is less than negative 5 is less than h of 1. Did we do that? I think we did, except instead of calling it h of 3 and h of 1 in our justification, we called it negative 7 and whatever. But is it okay to use the numbers there? If they're labeled up here clearly? Heck, yeah. Yeah, you can, absolutely. And then it says, you do have to say it's continuous. Now notice they didn't say continuous on the closed interval, they just said it's continuous, which implies that it's continuous where? Everywhere. I would beseech you to speak directly to the theorem, because again, it demonstrates, I think, more knowledge of the theorem. By the intermediate value theorem, they spelled it out. Do you have time for that? Maybe. Is it necessary? No. EVT, IVT, MVT. Those are all name brands. You can use them. There exists a value R, blah, blah, such that. So you got 2 points. Great. So that was a review of the EVT. Let's look at Part B. Part B. Explain why there has to be a C value. Whoa. Between 1 and 3, such that H primacy is negative 5. They sure like negative 5. Whenever you're trying to prove that a certain derivative value exists, as opposed to a Y value, you're not going to use the IVT, you're going to use the MVT. The MVT is good for proving slopes exist. The IVT is useful for proving Y values exist. Got it? IVT, Y values, I, Y, they have the same I sound. And MVT and slopes. Where do we associate slope with the letter M? Algebra 1, right? The French verb to climb a mountain. Which is what? Monter, right? That's where the M comes from. So MVT, slopes, and IVT, Y, IYM slopes. Got it. All right, so I'm going to get rid of all this stuff up here because we need the space. Don't do this on the real test. Don't do A and then erase it. Keep it there and just go to Part B. All right, explain why there has to be another X value where the slopes are negative 5. How are we going to do that? Well, as we go from 1 to 3, let's just go ahead and say f of x is continuous on the closed interval from 1 to 3 and differentiable. You spell it out. Let's pretend like we're there. Differentiable on the open interval from 1 to 3, comma, so the MVT applies. So now you have the full authority of the MVT, and the calculus cops are going to back you up. All right, let's find the average rate of change. We know that f prime of x has to equal f of 3 minus f of 1 over 3 minus 1. Somewhere between 1 and 3, there's an x value that makes it work. Now, do you have to call it c, or can you leave it as x? You can leave it as x, okay? But we're just saying the derivative equal to the average rate of change.
You can't accidentally put c anywhere else, or she was correct with that, right? Like if you accidentally put f of c on this line, then it would.
No, you could actually. This is actually where you might actually want to put f prime of c.
Oh no, but like I'm saying, if you put f of x first, f prime of x, you couldn't switch to f prime.
You probably could, yeah, because you could without any consequence.
Oh, you could.
Yeah. I would try to be consistent, but if you call it f prime of x here and the next one you call it f prime of c, that's fine. And that's fine. You wouldn't be deducted for that. If you were, I would call the calculus cops, and they would take care of it. But you do try to be consistent. What I'm doing is I'm just solving it in general, and then at the end I'm going to declare that the x value that I found is the c value they wanted. Okay. How do I find f of 3? Do I need to plug it into? Oh, I need to plug it into h. I'm getting ahead of myself. We're trying to prove that h prime exists, so let's back it up. Good thing I caught that. H prime of x equals h of 3 minus h of 1 over 3 minus 1. There you go. That's better. Yeah. Now, h of 3 and h of 1, what the heck are those? We have to compute those. Do we have to compute them all over again? Or can we import them from part A? You can import them from part A. H of 3 was negative 7. H of 1 was 3. So negative 7 minus 3. I would just show that. Negative 7, minus 3. Don't call it negative 10, because if you call it negative 10, we're going to be like, where'd you get negative 10? But if you call it negative 7 minus 3, and it's labeled like this, we're like, they imported from part A. All over 2. Do we need to show a difference quotient on this line, or did we already show a difference quotient? We already showed it. So, yeah. Let's simplify that. That gives us negative 10 divided by 2. That's negative 5. We're trying to prove that the slope equals what? At least one place? Negative 5. By the mean value theorem, we got negative 5. So, by with a B, by the MVT, comma, and what are we going to write next? There must be a value C. There you go. That's it. So for the IVT, it's about saying it's continuous on the closed interval, computing the y values at the endpoints, and saying the value you want is in between there. For the MVT, it's all about finding the difference quotient, and that's it. And then saying then there has to be some value. How many points is that going to be worth, do you think? I hope at least 2. Yeah. Yeah. And they said it's continuous and differential. Again, they didn't speak specifically to the theorem. They're claiming that it is everywhere. That's kind of a bigger claim. So try to speak to the theorem. And they are using the same word. So that's 4 points right there. And if you were getting 4 points when the average was less than 1, you're a shining, bright star. Yeah. Now let's see if we can do part C. Let W be the function given by W of x equaling the S. S. Okay, I'm not going to do that. If G to the negative first is the inverse of G, well, you know what? If I can't do C, then I certainly can't do D. I'm walking away right now. Is that the right attitude? Is that the right attitude? I'm walking away. Is that the right attitude? No, because sometimes they're totally not even related to each other. Look what D says. If G inverse is the inverse of G, write an equation for the tangent line to G at 2. Okay, so what do we need for the equation of a tangent line? Slope and a point. So I need on G inverse there's an ordered pair called 2 comma something. It'll be G inverse of 2. And I also need the slope. I need the slope G inverse prime of 2. How am I going to do that? G is the inverse of G, right? So if there's a point on G inverse called 2 comma something, then on G there's a point called something comma 2, right? So let's go up to the table and look to see where the y value of G is 2. There. Yeah? What's the corresponding x value? 1. Okay. So I know that there's a point on G called 1 comma 2. So there's a point on G inverse called 2 comma 1. Yes? 1. And if I'm trying to find G inverse prime of 2, that should be the reciprocal of its inverse G prime at what? 1. Oh boy, now I have something with which to work. All I have to do is find G prime of 1 and flip it. Let's go to the chart. G prime of 1. It's going to be what? No, that's G prime of 2. Oh, I see why they put the 1 there, though. Really do. I see why the 1's there. G prime of 1 is 5. So the answer should be what? 1/5. And notice my notation is kind of all intact.
You should work out C just like as foreshadowing.
We got 3 points for that. Oh, we didn't write the equation of the tangent line because we got excited. But how easy is that going to be? That's going to be super easy. Just drop it in the Taylor form. They have point slope form. We would use Taylor form. Y equals 1 plus 1/5 x minus 2. Okay, now we got all 3 points. Pretty awesome, huh? So how many points are we getting on this one? 4 plus 2 is 6 plus 2 is 7. So we got 7 out of the 9 points. You want to do this as foreshadowing?
Yeah. The little explanation was that complicated.
Okay. Does anyone else want to do part C as foreshadowing? Yes. A harbinger of things to come?
Yeah, whatever.
Whatever. All right. Let W be the function given by that. Find the value of W prime of 3. Okay, not a big deal, right? We always begin with the end in mind. You ever done those mazes, those puzzles with mazes? You always begin with the end in mind. You start on the outside and work your way back in. It's a lot easier. And then once you get to the center, then you can go forward and follow what you, yeah. Is that cheating? I don't know. That was a horrible analogy. It doesn't really relate. So, we want to find W prime of 3, but before we can do that, we need to find W prime of the independent variable, which in this case is T. No, it's X, sorry. W prime of X. All right, so if W of X is the integral from 1 to G of X of f of T dt, did you hear how I said that? The integral of, that terminology will be coming. I'm going to take the derivative of both sides. The derivative of the left is W prime. The derivative of the right side with respect to X is going to be the integral from 1 to G of X, f of T dt. And then I have to implement that. T, thank you. So W prime of X. It turns out that the integral is a multiplicative process. You see that? F of T times dt? See that? It's multiplication. The derivative is what process? Division, right? dy dx, dy divided by dx is division. Integration is going to be multiplication. The derivative is division. How are multiplication and division related? They're inverses of each other. So these two things undo each other, and you're left with f of, you're going to plug in the top for t, g of x, times the derivative of what you plugged in, which is g prime of x, minus, you can do the same thing on the bottom, f of 1 times the derivative of what you plug in. But what's the derivative of 1? 0. So you end up with w prime of x equaling f of g of x times g prime of x. And now all you have to do is plug in your value of 3, and w prime of 3 would equal f of g of 3 times g prime of 3. And now you can pull values from the table. G of 3 is what? 4. And now f of 4 is negative 1. So this becomes negative 1 times g prime of 3. G prime of 3 is 2. And at this point, I'm walking away right there. Oh, I messed it up. I put negative 2. Let's stop right there. It's negative 2. It's still correct. And you got 2 points for that. One for applying the chain rule, and one for your answer. Yeah. So this is where we're going to be getting to soon enough. The integral ends up being the antiderivative, which means going backwards. And the integral and the derivative are inverse operations of each other. That's the fundamental theorem of calculus. So just like when you multiply by 5 and turn around and divide by 5, you end up with the same thing you started with. We're starting with a function f, and we're ending with a function f. But there is some chain rule stuff going on that you'll understand when I teach it to you more in depth. But if you followed that, that's great. Hey, what if things to come? It geometrically turns out to be the area of the region. Yeah. Okay, awesome. So now we got all 9 out of 9, and the average people are getting 0 or less than 1. So yes, I will work one on the worksheet. Should we record the discussion?
Yeah, I was going to say, what are you going to name this?
I don't know, just kind of hodgepodge oleo. We're going to call it oleo. What section are we on? What is it, 4 point something? I don't have it downloaded yet. She wants to work one from the worksheet. Yeah, so let me download it. I haven't done it yet. Was it all multiple choice? Oh. I've redone all the worksheets from last year up through, I think, optimization is kind of where I was like, ooh, the summer's ending and I ran out of time. Yeah. Oh, are you referencing a previous document? Oh. Yeah. I like to keep it fresh and real. Which one? I terribly don't mind eternally. Consider the following statements. Number 1, f is continuous in the closed interval. Ooh, I've heard that before. 2, f is differentiable in the open interval. Ooh. So now I'm thinking after number 1 that the IVT and the EVT apply. After adding the second condition, I'm thinking MVT applies. F of A equals F of B. That means the y values of the endpoints are equal. Now I'm thinking whose theorem? Rolle's theorem. Yeah, Rolle's theorem. Not Colin Rolle's theorem, but Michel Rolle, right? Which of the following statements are required in order to guarantee an x value between A and B such that f prime of C times B minus A equals B minus F of B itself? What the heck is that? It looks very similar. Yeah, if I take this and I just divide through by B minus A, I get F prime of C equals F of B minus F of A all over B minus A, which is the MVT. So yeah, it was just in a different format. And this will be a little bit more important when we get to the fundamental theorem of calculus. But right now, knowing that it's the MVT, we know that for the MVT to apply, 1 and 2 have to work. And the answer is B, as in I am bursting with bataquatulence. Bursting with bataquatulence. I don't know. Can you tell from my demeanor what bataquatulence is? Because I'm bursting with it. Speaking of bursting, we read the Worst Fest yesterday, right? That we read the Worst Fest limerick. Did we read it out loud? Oh, we didn't. Okay. Worst Fest jetzt has now come to town. Lederhosen und Dirndls, not long pants and gowns. But try not to burst. Eating way too much wurst, or drinking so much that you drown.
The last one was kind of dark, yeah.
Well, I wrote that after experiencing everything that I saw on social media, like the first 3 days of the festival. And no one was posting like empty sausage sticks. Look, I have 52 empty sausage sticks. Oh, no. It was like I have 7 empty pitchers, right? Or 32 empty cups. It's Worst Fest. It's not Cerveza Fest. That's a different fest. But anyway, what is German? Beer. It's beer. Yeah, Beer Fest. Yeah. I saw a guy wearing a shirt. It was the Jeep logo upside down. The Jeep logo upside down. No, what is his? That's what it was. His shirt said beer, but it was written in the. It looked. It was the Jeep logo. It was like written in Jeep font, but it was written upside down and it said beer. And I didn't want to ask him if I could turn the shirt upside down, but knowing now that his shirt actually said beer in the Jeep logo, it wasn't the Jeep logo upside down, because I don't know what that is. Man, he got me. He got me good. That was probably only because I was probably into my 5th sausage stick by then. No, no. When you're there, you can buy pitchers at a time of like Coca-Cola and lemonade and water. I'd like 3 pitchers of water, please.
Is that why you're a little behind on?
No. I'm actually on a no alcohol diet for over a year now. So I did go and just smell. I smell. Yeah, but I did have sausage. I did have the pork wings. They were pretty good. If you haven't had those yet. Oh yeah, I had those last year. Yeah. They're still good. They make them fresh. Yeah. They're not the same ones. All right, heat up all the leftovers from last year. I don't know if there are leftovers. They sell a lot of stuff.
I went to work last year. I don't know what I ate, but I think it was sick.
Uh-oh. You must have eaten something bad.
Yeah, I don't understand. Where do you go and where's this to not get sick? Everybody's talking about all this great food, and I went like, dude, I'm throwing up.
Go inside the building. Those other little vendors down there at the bottom, they're kind of like, you could buy like fried everything with like a potato thing wrapped around it.
Fried everything with a potato.
Yeah. So just go inside and go to the smokehouse booth. Go to the Rotary booth. They have the Wurstentaschens. The sheriff's booth. There's a place right there. The Noon Lions. Every time you get something at the Noon Lions booth, it's the yellow booth. They're so sweet there. They give you a little button every time, a free button. Yeah, and they're so sweet. That's the Worst Fest hat. That's the Worst Fest hat. Yes, I'm still recording. Yeah. So if you're listening, if you can get here by next Sunday, we have Worst Fest going on. What? Is it going to be titled like Worst Fest video now? I don't know. We can. Let's stop the recording. Yeah. Let's stop the recording. Go ahead and download the next notes if you haven't already for 3.3. You can go to the restroom, yes.